Hi guys, I'm Megan Jordan, and today we will be doing uphill without slipping. A cart of mass m equals 47.5 kilograms is getting ready to carry a crate of mass m equals 14.5 kilograms up a slope of angle theta equals 30 degrees with respect to the horizontal. The wheels of the cart move freely without friction in their axles, and they do not skid over the incline. The coefficients of static and kinetic friction are 0.7 and 0.5 respectively. The system is subject to the regular force of gravity. The car is initially at rest, while a rope under tension T that is parallel to the slope balances its down ramp tendency of motion caused by gravity. At T equals 0, the magnitude of the tension starts increasing linearly at a rate of 11.5 newtons per second, and the car accelerates up the slope. For my part, I'm going to determine the work done by tension between T equals 0 and the moment the crate starts sliding towards the back of the car. So that's going to be part A. Okay, so I've got everything drawn out and written out so that we can kind of see what's going on. We've got our picture, our free body diagram. We've listed out the given information of the masses and slopes, coefficients, and such. All right, so we want everything balanced out because we're in at a static point. We're not moving yet. We're at rest. So I've written out our formula here: coefficient, static friction, mg cosine theta equals ma plus mg sine theta. So if we move everything around, include what we have, we get acceleration is equal to g times, since g is multiplied times all of this, we'll put it in parentheses. So static friction cosine theta minus sine theta. Okay, so we know 11.5 T is equal to the mass of the system times gravity times, as we said earlier, coefficient static friction cosine theta minus sine theta. So let's get T by itself by dividing everything by 11.5 and then plug in our number. 62 is our 47.5 plus 14.5, our masses of our cart and crate, times gravity times 0.7 cosine 30 minus sine 30 all over 11.5. We do the math on that and we end up with T equals 5.6158. So let's go back. 11.5 T equals the mass of the system times acceleration. So let's get the A by itself by dividing the mass of the system, 11.5 by the mass of the system. So plug those numbers in, and then let's find velocity by integrating everything. So if we see down here, we end up with 11.5 over 62. So ultimately, once we integrate it, times t squared over 2. But to make it a little neater, let's multiply this 2 and this 62, and so we end up right here. So we found our t earlier, so we can plug that into our system, and 11.5 over 124 times 5.6158 squared, our velocity gives us a velocity of 2.9248 meters squared. So let's do the same thing. Let's integrate again for our speed. So we end up with 11.5 over 124 times t cubed over 3. Multiply that together, make it a little neater. So we get 11.5 over 372 times, again, our t is 5.6158, and that's cubed. So our speed is 5.475 meters per second squared. All right, so our initial kinetic energy, well, we started at rest, so we know our initial kinetic energy is going to be 0. Once we plug it in the formula, multiply times 0, that's equal to 0. Our final kinetic energy is going to be a little different. 1/2 times our masses times 2.9248, which is our velocity, and we're going to square that. So that ends up giving us 265.1881 joules. And since our initial kinetic energy was 0, once we subtract 0 from this number, we get delta K. So delta K is equal to the same as our final kinetic energy. So we need to find our work done on gravity, by gravity, So we take negative mass of the system, g sine theta times speed, and we get negative 62 times 9.80665 sine 30 times our speed, which we found earlier is 5.4751. So that ends up giving us our WG, our work by gravity, is negative 1,664.464 joules. But the problem wants to know what done by tension. So if we take our total work and make that equal to delta K, we can find that answer. So since we have WG, we'll take work done by gravity of negative 1,664.4641 plus our WT is what we're going to find, and then make that equal to kinetic, the delta K, change in kinetic. So we know that was 265.1881. Well, we need to get WT by itself, so let's add 1664 to both sides. So that ends up giving us work done by tension is equal to 1,929.6522 joules.
Hello, I am Vivian Garcia, and I am doing part B of our sliding uphill without slipping, I think it's called, sliding uphill without slipping problem for our final. So, for part B, it asks us, determine the change in kinetic energy of the crate between time equals 0 and the moment it starts sliding towards the back of the cart. So, I'm going to put my little face here. So, the first thing that we have to start with, because you're gonna, as you can see, you do a lot to get to the final answer. First, we have everything given right here. And so these are all our givens, and here's our little graph. I'm sure this was already showed in previous problems, part A. So, first we start off with the initial tension, and we have this equation, the initial tension. The reason why we have big M plus little m times g sine theta is because both of these are m, the mass, times g sine theta. And so we basically factor out the m's, and this is big M and that's little m. So of course, you have that equation. Then we also were given that with this derivative, it equals 11.5 newtons per second. And then the tension at any time is t, little t. So, start off with this equation, and as you can see, since we already found the initial tension, that can be plugged in, and we plug in this. So now we have tension overall tension. So, then, for the next equation, we have the force equals mass times acceleration, of course. This is mass times acceleration. Again, we're adding the masses. But for the force, we have our handy-dandy little x-axis right here. As you can see, it's going up because the cart is going up before it slides back down. So, the cart slides up, and with it sliding up, the tension is positive because it's going along with the x-axis. But since the mg sine theta is going against it, it is negative. So now we have the tension minus all this good old handy dandy stuff. Then we're going to plug in t. So since we already solved for t right here, this part can be plugged in, and that's this. And then it's minus the mg sine theta equals the acceleration, or mg mass times acceleration. But since this is negative and this is positive, they're canceling out. So now we're left with 11.5 t equals big M plus little m times acceleration. With this, we go right into our next part. We have this that we got directly from our little graph, and then of course we have the force of static friction equation, which is the coefficient of static friction times the net force, which the net force becomes mg cosine theta because that's what's being pulled down on this slope. So, setting these equal to each other, you can see that you, of course, cancel out the masses. That gives you solve for acceleration. You plug in, because you can just rearrange this, the acceleration, and then of course you multiply out the m plus m to get 11.5 t. Solve for t, and then you get t. Finally, after that, we have our t, and we're going to start finding velocity. To find velocity, we're solving for a in this problem again, as you can see right here, and we're plugging everything in. We already plugged in our masses, we derive, and then we get velocity times t squared. So after that, we have a velocity. Then for initial kinetic energy, we have kinetic energy initial and final, which is equal to 1/2 mv squared. Plug those in. Then you have, for the whole thing, the whole kinetic energy, you have kf, ki, and then you solve, and you get the final answer. Thank you.
Hi, my name's Brianna, and I'll be discussing part C of Uphill Without Slipping. First, let me share my screen real quick. All right, so part C, we are trying to determine the magnitude of the acceleration of the crate with respect to the fixed incline when it is sliding toward the back of the cart. So little m is the crate and big M is the cart. All right, so first we'll start with Newton's second law, which states a body accelerates when acted upon by a net external force. This comes in the equation of force equals mass times acceleration. From that equation, we can replace force with the kinetic friction minus mass times g times sine of theta. The kinetic friction is the force between the crate and the cart, and it is going towards the x component I've drawn in my little drawing here. mg sine of theta is negative because it is in the opposite direction of the x component of the system, and that gives us the total force. From that equation, we can then replace f of k with the coefficient of kinetic friction times mass times gravity times cosine of theta. And then we can plug that back into the first equation to get this equation. And from there, we can get acceleration by itself by dividing the mass to the other side, which cancels out all the masses. And then we can take out g, which leaves us with acceleration is equal to g times the coefficient of kinetic friction times cosine of theta minus sine of theta. Then once we plug in the numbers, we were given acceleration equals 9.80665 for gravity times the coefficient of kinetic friction, which is 0.5, cosine of 30 minus sine of 30. We get the final acceleration of 0.6569 meters per second squared. And that is how you find the acceleration of the crate.